thanks to AE for putting this together. I'm assuming that the audience that we're going to be speaking with today is generally comprised of either people that are, selling and trying to present solar plus storage systems and or installing these systems. So I'm going to make some assumptions in terms of just technical understanding of the battery systems and the like. Today in the presentation, what I'm going to try and cover off with you is just some of the fundamentals. Lithium storage is fairly new, and even if you're an experienced battery-based installer, the transition to lithium offers some challenges and some real opportunities. So I'm going to try and make this as little sales pitchy as possible and just try and give you general information that you can take away to do comparisons on your own, answer your clients' questions, and help you to gain the tools and necessary tools to effectively design, install, and recommend battery-based systems. Just a quick overhead before we get going here. Discover is DNA is lead acid batteries and energy storage for many markets that way. The lithium portfolio obviously is fairly new, but we've been designing and selling through AE to the solar specialty market for past 3 years now, and the product's really mature. So some of the things I'm going to be speaking to you today are just comparing and how to evaluate batteries based on spec sheets and published data, so you understand what you're getting into and what you're recommending for your clients. So without further ado, here's the general overview. We're just going to be going on the type of things and the basic math you'll need for comparison tools. Then I'm going to go a bit into the fundamentals of cell block and BMS design, as those are critical capabilities and critical components of a lithium battery system that are unique to digital batteries, electronic batteries, as opposed to old lead acid batteries. And then we're going to go into some of the comparisons and what to look for on data sheets. Okay, we'll move forward here. Here are some of the fundamentals for you. And as we get going, please, there is a question tool on this. I'm used to doing this in a live environment and getting some participation from the audience. So in lieu of the fact that I can't see you with your hands up, please feel free to jump in questions as you go. If I skip over a topic that you're not really clear of, please just put your virtual hand up and ask the questions, and we'll try and address them at the appropriate time. So a well-designed lithium battery, okay? It should be designed to take advantage of the optimal advantage of the lithium cell, okay? And some of those characteristics are the fact that it recharges very, very quickly, that it has a very stable voltage profile, so it's able to provide a continuous voltage for your loads and the inverter systems it's working in conjunction with throughout its charge cycle and state of charge cycle. Obviously, lithium cells are one of the primary pitches in moving from lithium, from lead to lithium, is that these cells will last a long time. In order to do that, however, there are some fundamentals on sort of charge, discharge, and keeping care of the batteries that are fundamental components of the BMS design. And a good battery will have a very well-designed BMS to complement the cell block. A good lithium battery will also work just as well on and off grid. And a lot of those things, we'll touch on those, but a lot of those are with regard to requirements for being and maintaining online access, in other words, internet connectivity. Secondarily is that, even if the battery does have comms, if the comms fail for whatever reason, the battery should still be able to operate and provide power just as it would before, just maybe in a little bit of a limited capacity. But it's critical that that energy storage and energy source remains accessible to you. It should ensure all the functionality that's based into that core inverter charger platform, and whether that's Solarc, Schneider, SMA, Outback, any of those groups, those are really complex pieces of power electronics with a bunch of features in them. You should be able to, by porting over and changing your customers from lead to lithium or designing a new system with lithium, you should be able to take advantage of all those baked in features and functions in the power electronics, and it shouldn't limit your ability to provide power and utilize all those electronics. And then finally, is that the battery is safe. And by safe, it's not just an opinion, you know, do I feel safe with this? There are some regulatory standards that are appropriate, and the NEC specifies those. So in this particular case, the UL markings we'll be looking at are UL 1973, which is the applicable standard for lithium batteries in a stationary environment. And then moving to, and what we're evolving to now, is a UL 9540 approval, which will start taking place in terms of enforcement in 2021. And I'll kind of allude to what that is with you later on, but that essentially is a standard for the system as a whole. In other words, matching the storage with a certain fixed set of power electronics and making sure that system is designed and approved to work together. Okay. One of the core pieces that we're going to be, I just want to go over some math with you here, but it's one of the core pieces to evaluate the performance of a lithium battery is its C rate in terms of rated amps in and out of the battery as a percentage of the battery capacity. Okay, the C rate enables you to look at a battery despite its size. For instance, our battery is a 7.4 kilowatt hour battery, you know, rated to 6.65 useful capacity of that. That is obviously a different format than, say, a Phi 3.8, which is 3.8 kilowatt hour battery. In order to compare those batteries on an apples to apples basis, it's best to look at their amperage and current carrying capability as a percentage of C, or their overall capacity. That normalizes it and takes out the capacity differences so you can assess what a battery's capability is to carry current. The reason this is important is that with a lead acid battery back in the day, those, I mean, say what you will about lead, but lead offers you the ability to basically take away current from any kind of design considerations, because they can handle and put out very high current rates for short periods of time in a very rapid response rate. And all of the modern power electronics that you're dealing with, again, with the Radiant platform and XW platform, SMA's Sunny Island, those were all originally designed to work in conjunction with lead, and they as a result, you know, they relied on the fact that lead could provide instantaneous power. Okay, so what I'm going to do here is just quickly go over with you the math on this one so you can see it. But the C rate when it comes to current is basically just the current rating of that battery divided by the battery's amp hour capacity. So in our case, again, looking at this, our rated amps DC in and out on a continuous basis is 130 amps. And it happens to be 130 amp hour capacity battery. So that would make the C rate 1 over 1, or 130 over 130, which is 1 over 1, or just 1. So we have a 1 C rated battery. If, for instance, the battery we had was only capable of handling 65 amps current, okay, 65 amps current over 130 amp capacity battery would make a C over, or a half C, or C over 2 battery. This is important when you start adding multiple batteries and you start looking at the capabilities or the power draws of any given piece of power electronics. We're going to go through some real examples there, but I just wanted to set the stage with you here. When I talk about C rate, it is a proportion of the battery's ability to handle current divided by its amp hour capacity, or its overall kilowatt hour capacity, if you want to take the voltage in consideration. Okay, so if there's any questions in that, we can answer those, but I just wanted to set this table. It's some basic math, and it's really pertinent to any discussion about lithium, because lithium batteries are limited by the current that the BMS can handle. Well, the fundamental lithium cell capability, but that's usually not the hindrance. They're limited by the BMS's ability to handle current on a sustained basis. So the next slide. And that was supposed to be hidden. So here is basically the architecture of a modern lithium electronic battery. Okay, you have these lithium cells. In this case, we're talking mostly for off-grid systems and things with lithium ferrophosphate cells, which is your LiFePO4 chemical name. Those individual cells are 3.2 volts per cell in terms of their nominal voltage. And what happens when you're designing a 48 volt nominal battery is generally what we're doing is we're taking a string of 16 of these cells, which if you do the math, 16 times 3.2 equals 51.2 volts DC. You get those in blocks, and then you combine n number of parallel strings to just increase your capacity and expand that capacity. In our particular case, if you look at that battery in the middle, that's just our Discover AES 48 volt big 7.4 kilowatt hour battery. You can see the cell configurations there. Those are 16 cell strings combined in multiples. Okay, of those, there's 26 parallel strings in this particular case, and that will blow you out to a 7.4 kilowatt hour, 51.2 volt nominal battery. Okay, as a comparison there, you can also see the inside of the Simplified 3.8 lithium ferrophosphate cell block. Obviously, slightly different build design, but the cells, you can see them, they're stacked in fours. That's the telltale sign that they're put together in 16 cell strings, and that's how they're combined. Now, again, there are some visual things I could go into on this in terms of if you look on the right-hand side of our battery, you'll see all the large buses that they're connected to. Those are just factors that allow for high current carrying capability, and they don't restrict the native capability of those cells. But overall, I wanted you to get an idea of how these batteries are designed, so you can see that these design considerations all add up to the ability for the battery to either A, provide or receive current, or B, manage that battery in relation to its power electronics, handle things like the digital communications and otherwise. Okay, when you go to the BMS design, which is the second piece, the BMS will sit on the cell block itself, and that BMS will manage all of the the faults, warnings, temperature considerations, etc. of that given battery. They will oversee any of the cell balancing. Again, we've got hundreds of cells potentially in one of these batteries. They do need to be balanced, just like cells in a large lead acid string. When you're talking about 6 volt cells combined in 8s to make 48 volt, there is a balancing factor that goes on between all of those small cells. The BMS will handle and manage that. It also takes readings based on temperature of the cell block in response to those. And in some cases, like with our battery, there's a comms board on there as well that allows for external communications with devices. You can see on a BMS, this on the left-hand side of this image, there are sort of small or off-the-shelf BMS designs that are designed to take all those cells inputs, manage that current, report faults and warnings, do solid-state switching and otherwise. The smaller BMS, though, typically becomes a bottleneck when it comes to current. As you can see, just in the componentry on the BMS on the left, there is far less copper and conductive material in order to pass current and allow for current flows than there would be in a larger BMS design as you see on the right in our Discover AES, for instance. You can see the big bus bars on the right-hand side, the big lugs, those aluminum extrusions on the top. Those are essentially just heat sinks that allow for dissipation of the current they're sitting right over a FET board, and that's effectively our switch, our digital switch that allows for control of the battery on and off. All of the current goes through these components. So if you have a BMS that's capable of high currents, you typically can allow yourself the most out of that given battery in terms of and those lithium cell stacks in terms of their ability to either provide or receive current. Okay, as we'll see on the left there, the smaller BMS in this particular case, the cells are and the cell blocks in both those batteries are very similar. They're all lithium ferrophosphate cells, so they should have the same characteristics. In this particular case, though, you can look at a BMS being the throttle or the bottleneck on the current carrying capability of that battery, and just simply, having limitations in terms of how much current can go in and out. Fundamentally though, if you want to look at a given capacity of energy storage, the easiest way for you to look at this is outside of design parameters. A battery that is rated for C/2 or a half C current carrying capability will require typically twice the recharge time of a battery that's rated at 1C. Okay, this is really important for off-grid systems when you might have other sources of power that run on fossil fuels, like a diesel genset, a propane genset, an LNG genset, or otherwise. So, again, the BMS allows the battery itself to take advantage of all of the native capabilities and performance of those lithium cells, and the two have to be sized and designed together to get the most out of those lithium cells. Okay, so what we're going to do now is I'm just going to show you the fundamentals of what you would do. Again, every one of these lithium batteries that's approved and rated through UL will have a battery spec sheet that is actually fixed. It has to be representative of what that UL approval is. So for the most part, if they've got a UL approval on their spec sheet, on the battery spec sheet, you can assume that the electrical specifications on their data sheet is accurate. Okay, that being said, here are some of the core things that you want to look at when you're looking at a data sheet and what they mean to you. So first and foremost, we'll start at the top right and we'll work our way down and then go back over to the left. But you see open circuit voltage, 51.2. Well, that is again 3.2 volts per cell times 16. The reason that's important is in some cases, particularly you'll see in telecom lithium batteries, instead of a 15 volt cell or 15 cell stack, they'll see 16, pardon me, you'll see a 15, which equates to 48 volt nominal. That is great for some applications like telco, but it doesn't really work in the off-grid world or the grid-connected solar plus storage world. You'll see the nominal energy there, 7.395 watt hour, or 7,395 watt hours is 7.395 kilowatt hours. That in turn relates to an amp hour capacity. That is just simply the 51 volts nominal taken out of that. That gets you 130 amp hours. And then here's the critical component that we looked at before in terms of C rate analysis. We have a continuous current rate of 130 amps on a 130 amp hour battery, which equates to 1C continuous charge and discharge. The peak current below, if you want to look at that, would be, I'm going to say 2.3 C, 300 amps divided by 130 amp hours. Okay, that's the ability for the battery to provide instantaneous power in response to like inrush loads that the inverter might be asked to power from time to time. The final thing we're going to look at with any battery is the UL standards that it's got rated to. This basically ensures that the battery is designed and tested to be safe in the application you're using it for. As I mentioned before, in this particular case, the relevant UL standard is UL 1973, and that's a battery standard inclusive of the enclosure, the cell block, the BMS, and it's all been tested for use in this particular application. You'll see next to that we also have a UL 2271 approval, and that's not relevant for solar installations at all, but it does show you that this battery is also approved for use in light electric vehicles. Okay, we use this battery in dual purpose for things like forklifts and golf carts, et cetera, et cetera. So these are the core pieces you want to look at with any battery and the fundamentals you want to take away from the battery spec sheet. For the next example, we'll do the exact same thing with a Simplified 5.38. So here's the battery, here's their spec sheet. Right from there, it's just a cut and paste from their battery spec sheet. And as we start to go through this in detail, I want to show you again. So the DC voltage on this, 51.2. So you can see they're using 16 cell strings. That's great. The amp hour capacity at 75 amp hours. If you want to do an analysis on that, it's 75 amp hours times 51.2 volts DC, and that'll get you to their 3.8 kilowatt hour nominal capacity of that battery. Now, where we start getting into some fundamentals, and these are important concerns, and we'll go through the design implications of that afterward, but we start seeing their max discharge rate, 60 amps. Max discharge 60 amps over a 75 amp hour battery gets you to somewhere around a 0.8 C on their peak. Again, comparing that to the battery we just looked at prior to this, the Discover AES, where we had a 2.3 or 2.2 C capability. This one at its peak is 0.8. We look at the continuous discharge rates now, 37.5 amps for discharge, and for charge, take 37.5 and divide it by 75 and you get your half C rating. So again, a half C rated battery means that on a continuous basis, they can only be recharged at half the rate of the Discover AES battery. Finally, we go down and we start looking at the cycles and warranties sort of things. These are important for you to look at because they both define the capacity, the useful capacity of that battery, and they have implications on warranty. So although this is a 3.8 kilowatt hour battery, because there's an 80% depth of discharge restriction on the cycle life, that means that in reality, you can only be using 3.04 kilowatt hours of this 3.8 kilowatt hour battery. And that's what you should be using for any of your economic analysis, like dollar cost per kilowatt hour or otherwise. But essentially, it's a 3 kilowatt useful battery. You'll notice that the regulatory approval, again, it's approved to the correct standard, UL 1973, so you can tell it's designed for that use. So we're going to go on now, or we're just going to have a look at the next battery in the lineup just to get you in a rhythm of what to look at on these. The next battery I'm going to do is the bigger Fortress battery. It's their LFP10 battery. Looking through the spec sheet on this and getting into detail, here are some of the things to look at. So this is a 200 amp hour battery. It's a bit, bigger than the first one we saw, and definitely bigger to a factor of 2.5 times what the Simplify is. It's a 200 amp hour battery. The charge current on this is a rating of 80 amps DC. So when you can do that math, 80 divided by 200, you have a 0.4 C battery. In proportion to that, it's going to take over 2 times longer to recharge this battery if you have the current available. And the max pulse current, I think it's supposed to be plus or pulse current, not plus current, but that's their peak current rating. That's rated for 180 amps. 180 amps over 200 amp hours is a 0.9 C maximum or peak current. Comparing that again with Simplifies, their 60 over 75 was about 0.8, and on the Discover side we had a 2.3 times C current carrying rating. So there's definite differences that are restrictions of the BMS themselves and not the cell blocks. Furthermore, as we get into this battery, please pay attention to the regulatory approvals. So this battery is approved to a 1642 rating. Well, 1642 for UL is a rating that's particular to the cells themselves. It means the cells have been UL approved, but it means that the battery as a whole, the combination of the battery cell block and the BMS, has not been approved to the applicable standard for stationary energy storage as defined by the NEC. So this is where you're going to have to dive in and typically raises red flags with your AHJ or your inspector. Furthermore, here you can see some of the things that's related to warranty. If 5 or 10 years, that is usually a function of the depth of discharge you want to design that system to. So in this particular case, it's 6,000 cycles at an 80% DOD rating. If you have 80% depth of discharge on a 200 amp hour battery, that's 160 amp hours of usable capacity. Okay, so that gives you the fundamentals on what to look for and how to generally look at a spec sheet and compare batteries. Now we're going to go into some of the implications for off-grid system design. Now, I used some references here that should be familiar to most of you that have done off-grid systems. There are, of course, other battery inverters. Solar Edge has battery inverters. Enphase has them now. Typically, those are for fixed use, and they're generally high voltage packs. these four brands and the inverters that are referenced here make up, I'm going to say, 80% of the market share in the North American market for hybrid inverter systems. Now, all have their pros and cons. All of have their strengths. I'm very familiar with all of them as I cut my teeth in this industry working in the inverter business. I worked for Schneider Electric for going on 17 years. So, you know, I've got a definite bias in terms of my internal knowledge, but these are my competitors, so I have to know them as well. Fundamentally, though, you'll see all of them have ratings for continuous AC output, peak AC output, their charger ratings, and then they have an efficiency rating. What I want to do with you is just show you some of the math on these as to how that has implications for battery sizing in a lithium world and why you need to pay attention to these. So on an installation by installation basis, whether you're a Schneider house, whether you're typically doing Outback, SMA, or Solarc, you should familiarize yourself with these ratings, because what they do is they have an impact on the current requirements of the battery bank that you're designing to go with it and mate with it. They will live together and are interoperable for the life of those systems. So it's very critical that you, once you choose your inverter platform, that you look into these considerations as they have definite implications on battery design. So going through these, it's pretty easy on the charger side. Okay, we've already determined that the charger for a Schneider is 140 amps DC. Now that is just the inverter charger. That's what it's able to produce as a DC charge output at, so you know, 55 volts or so, 140 amps. On the Outback, you see it's 135 amp charger. On the SMA, it's 130 amp charger, and then the biggest one of the bunch is 190 amps DC from the Solarc. Okay, that's fairly straightforward. It's a rating directly from their sheet because it's already converted to DC amps for you. The AC side is a little more complicated. In order to look at this for you, what we want to say is, we want to say on the Schneider, for instance, you've got 12 kilowatts AC. Okay, well, that's great, but you need to convert that into amps DC. So we're going to divide that on the lower end of the voltage spectrum, call it 48 volts. And then we're going to divide that current draw by 0.93 because we have some efficiency losses in there. And those efficiency losses have to be made up for with extra, you know, power from the batteries in order to provide that 12 kilowatts. So when I do the math on that, I take 12 kilowatts AC, I divide it by 48 volts, and then I divide it further by 93% efficiency. You get in a scenario where you have a requirement to meet that 12 kilowatts, you need to be able to provide 269 amps DC from the battery bank. Correspondingly, when we do the same rating for that Outback, because it's got 17, okay, it should be kVA, 17 kVA peak, it's a bigger output. You see a bigger discharge and DC requirement to optimize and be able to provide the full power that Outback Radian is rated for. SMA, again, 244 amps. It's the same math. It's just because it's got 11 kilowatt peaks, it's a lower number. And then when you go to Solarc, you see 20 kilowatts peak AC. Well, you know, again, that's a very large current discharge on that one. It's a bigger inverter, different sort of platform, but it's also got a higher efficiency. So you're basically, it's more in line or less impacted by the efficiency. But you'll see that every Solarc converter is capable of requiring 434 amps DC to provide that 20 kilowatt AC output. Now, from this point in time, you have those basics and outline. I'm going to work from averages of these platforms because we're not doing it, you know, inverter specific. I'm going to look at averages here so we can speak to the whole. But this characteristic, whether you look at a Victron inverter or a Magnum inverter, those same concepts apply, and you can do that math yourself. So here we go, and we're going to talk about the charger sizes from this now. This is specific to the charger outputs. I did an average from those 4 different charger ratings, you know, ranging from, I think, 130 amp to 190 amps. I added them all up, divided by 4, and we have an average here of 145 amps DC charger. Now, keep in mind, this does not consider other charging sources like DC coupled solar from charge controllers. Okay, those would be incremental. Now, typically they're not working at the same time as the inverter charger, but if you have two MPPT 80s, for instance, or two FM 100s, well then instead of charging to this 145 amps DC, you need to look at a rating of 160 amps DC or 200 amps DC to do this same analysis. We're going to base the numbers below on 145 amps DC charger, but be cognizant of the fact that if you have other external charge sources, you need to size to the maximum of whatever that charge source will be at any given time. In this particular case, we're just looking at the hybrid inverters. We'll use 145 amps DC. Now, by the ratings we talked about in the batteries when we reviewed them before, I want you to see that with the Discover AES on the far left-hand side, it had 130 amp continuous rating. So with sizing this for 145 amp charger, well, that's over what one battery can handle. Not very much, but it's over that. So if I want to take full advantage of the charger in my hybrid inverter system, I need to size a battery bank with a minimum of 2 of these batteries. That will handle 260 amps current. Okay, and given the battery's form factor and things, that gives you a gross capacity of 14.8 kilowatt hours, a useful capacity of 13.3, and that 2 batteries at retail, I just did web costing on this, that 2 battery stack is going to cost you, cost a consumer at full retail, roughly, almost $13,000. Now we're about to launch another battery, and I thought I would throw it into this mix so you can see how the sizing compares even with our own BMS design. This is a smaller battery bank that we didn't compare before. It's got a amp hour rating of 57 amps. So if I take 3 of these batteries is what it's going to take for me to meet the minimum of 145 amps DC. That will provide me with 171 amps charging capacity on a 9 kilowatt hour battery bank, and that's going to cost roughly $9,000. Moving along to Simplified, which most of you will be familiar with. Here, they have a current rating, a continuous rating of 37.5 amps DC per battery. So in order to handle the current of a hybrid inverter, you would need a minimum of 4 of these batteries in, working in parallel. You basically are linearly adding that 37.5 amps capability, and that gives you 4 batteries will give you 150 amps, which is over what you need for that hybrid inverter, and accommodate that. So the minimum kilowatt hour size is 15.2 kilowatt hours, and then the net is simply just 15.2 times their 80% at the discharge maximum. That system's going to cost you for 4 batteries just under $11,000 at, again, retail on these. I just did some web searching for street price. Next in the lineup is the Fortress, their new Fortress 5 kilowatt battery. We didn't compare this specifically, but the fundamentals still apply. This particular battery, has a rating in and around, I want to say 55 amps. So I think I did the math right there. Yeah, 160 amps, 165 amps would be the equivalent of 3 of those batteries in parallel. That again is over the 145 amp requirement for the average charger output. It's going to give you a gross size of 16.2 kilowatt hours and 13 kilowatt hour net. And again, that's going to cost at or around $12,000. And then finally, we'll get into the bigger Fortress battery. 1 battery can't do it. It's got an 80 amp maximum. So you need 2 of these big batteries to handle the 145 amps charging capability. Gets you into 20 kilowatt hour batteries, 16 kilowatt hours net, and it's going to be a $14,000 spend for your consumer. So what I want trying to relate this to you is what the minimum requirements are to meet this charger output and how those have implications on capacity and cost. If there are any questions on this, again, feel free to stick your hands up, but you'll start to see this kind of documentation when you get into warranty statements. For instance, when you see the design guide for a Simplified, they'll recommend 5 batteries for any of these big hybrid inverters. And on the next slide, you'll start to see where they get the 5 from. So now we're looking at the requirements for the peak AC discharge. This is handling AC loads and the surge from those inverter chargers. This is one of the reasons you're buying those big hybrid inverters, is to power loads that require large startup capacity, like motor loads, and basically handles inrush. We know that the average of these things, as we reviewed before, is typically 250 amps plus. I did the average from the ratings of these different inverter charges, and the average current draw at peak for these equates to 330 amps DC. Now, same math, same process for all these. I talked to you before about the current carrying, momentary current carrying or peak current carrying capacity of our Discover AES battery. On the 48 volt big battery we have, it's 300 amp rated. So again, I'm sticking there with 300 amps. If I parallel these batteries, I have the ability to handle 600 amps peak load, well over the 330 amps DC draw of any of those hybrid inverters. So with a 2 battery system, I can easily handle anything that those big hybrid inverters will throw at it. Okay, the capacity remains the same. It's 2 times 7.4, and the cost remains the same. You're probably just in and around the 13K region. You'll see now with our smaller battery that we're about to release here, I actually require fewer batteries than I did for charging the previous slide, right? Where I had a design limitation here at 3 batteries to handle the charge current. On the AC side, because this has a 220 amp capacity BMS for momentary discharge, I can accommodate the AC side of this with just 2 batteries. Okay, and actually I didn't even carry the math around. I've got that based on 3 for the ownership charge. With the Simplified battery, and here's I've specifically highlighted that amperage in yellow to point out something to you. When we did the average current draw for these systems at 330, it was weighed largely and buoyed up or increased over the 300 amp level because of that big solar converter charger that I think commanded 390 amps DC to run it. If we look at the normal installation for these and you look at their design guidelines, they recommend 5 batteries. Okay, that's because their peak current rating is 60 amps per battery. So if we multiply that by 5, we get to the 300 amp current carrying capability, and that is meets or exceeds what you're typically going to find from a XW Pro, a Radian, or an SMA Sunny Island. So I didn't round this up to 6, which would cover the 330 amps. I kept it at 5, but I wanted to red flag this and point it out to you that a system like this, although you can do it with 5 with most of those, if you wanted to go to a Solar inverter charger and take full advantage of their peak AC, you would again need to add another battery to this to get to 360 amps rating, and that would drive up your capacity and therefore your cost. Okay, so you can see the implications of adding batteries to accommodate current has an impact on the cost to the consumer. Going down the line with the Fortress batteries again, when you have 130 amp peak, as the Fortress 5 kilowatt does, it takes 3 of those batteries in parallel to be over the 330 amp current draw from one of those inverter chargers. That forces you into buying 3 of those batteries and again increases the price. Same thing with a big battery there. At 180 amps rating each, you would need 2 of those batteries at minimum, and that gives you a 360 amp hour capacity. But you'll see, now you're designing a system that has to have 20.4 kilowatt hours capacity, because in a single battery, the 10 kilowatt battery, it can't handle that current. You're driving the cost up and the minimum battery size up as well. Okay, if you all of these functions are driven by a combination of both the inverter's ratings and the amp current draw that you're converting to, and then what the current ratings of an individual battery are, because you're going to have to parallel those up to meet the minimums of the system requirement. Okay, it's a matching game, because in lithium you don't have this almost infinite ability to handle momentary currents, and you need to design your storage system based on the current rating of the BMS and the fundamentals of the lithium cells. Now, making this a little easier for you. It's always good to understand the fundamentals of this, but I don't do calculus or advanced math in my mind anymore or on paper. I do it with a calculator. We've done the same thing for you. Discover has a calculator on our main solar page, which you can find at www.discoverbattery.com/solar. And if you go to the top right of that page, you'll see a link to a battery comparison and cost calculator. If you drop in the fundamentals information of the system you want to design, and then the details of the battery you want to compare with ours, in the example here, you see a Fortress LFP10. You can fill in all that battery information from whatever battery you want. Battleborn, you can go to Lithionics, you could go to Pylon Tech. Take the data sheet yourself, so you're putting in the data yourself. It's not biased. We're not playing games and chip with math. Drop in the information for that battery, and we will spit out a nice report to you that you can hand off and print out, so you can hand off to your consumer to let them make an informed decision on why you're recommending a given battery or why they should go one way or the other. And typically it'll lead them to making a decision on your own rather than you have to do it. It also takes out your necessity to go through and do this math based on these systems. But you'll see the outputs there in a nice printed format, and essentially it's just a tool for you to use when you do this. It's available on our website. It's free of charge. It's there for you for design considerations, and I just thought I'd mention it here because essentially all of the math we're doing in this calculator is what I've just walked you through on the previous slides. Okay, so going into, again, some of the differences for traditional lead acid storage to advanced lithium systems we're using now, and again, getting back to the fundamentals, is that all of the hybrid inverters you're used to installing were originally designed with some assumptions in mind, because they assumed they'd be working with lead acid batteries. They assumed they could make analysis or some assumptions based on remaining capacity of that battery based on a voltage discharge curve. Okay, a full battery would be at a function of, call it 53 volts, and a battery that's declining would be linear. It's somewhat a linear curve, as you can see there in the gray side of that graph. That would give you a nice clean design to basically say at 48 volts, I have this much energy and or runtime available. Because the inverters themselves are electrically attached to the batteries, and they have these terminals that have voltage sensors on them and things, they're able to read that voltage. There was no need for communication between the battery and the inverter charger in order to get some estimation of how much capacity was remaining. Now, as you can see in the green curve that's there, a lithium cell's discharge curve is very flat, which basically eliminates the capability of these hybrid inverters to make the same assumption on it. And therefore, in the lithium world, you'll hear us talk about SOC, or state of charge, as a representation of how much energy is left in that battery. And we don't talk about VDC. Well, this is further complicated by the fact that all of those hybrid inverters used to use voltage triggers to do fundamental decision making, such as, at worst case, your low battery cutoff is shut off. At what voltage reading should I shut off this inverter to protect the battery from damage? Well, you had a variable number in there, and you could choose 48 volt as your trigger, and at 48 volt, if the battery was sustained there for a while, the inverter would shut off and say, hey, until there's a recharge source, I'm not going to turn back on because I'll damage these batteries. With lithium, you can't do that based on voltage, except at the very extreme edges, as you'll see. So what you're relying on there to do advanced things, and whether that's grid support, or whether that's turning a generator on and actuating a generator from a voltage trigger, or turning a generator off when the batteries are recharged, VDC simply doesn't work. You want to use SOC, and the only way for an inverter charger to act on SOC triggers is to have direct communication between the battery and the inverter. Okay, typically that's done with CAN communications, or Modbus, or Modbus TCP/IP, or RS-485, serial controls. But there has to be some way to communicate the battery's measured SOC, okay, which the BMS is doing and producing, and get that to the inverter charger so it can make informed decisions. This is why at Discover, we've put a lot of effort into integrating our batteries communications with the native communications of those inverter charger platforms. Without it, you have very limited ability to take full advantage of those hybrid systems, hybrid inverters, capabilities and controls, and you're relying on very edge case voltage ratings to make those things. So, you know, at the tail end, you'll see, you know, the ability for higher voltages to make some triggers, and at the very low end of capacity, you can do that too. Well, when you're reporting SOC, you can use triggers throughout the whole battery's discharge and make informed decisions that way. It becomes very critical. Not only that, but we can also push things like faults and warnings. We can be pushing things like temperature ratings. We can be actually doing command and control, and you'll see some of those things as I go through this and what those mean. But ultimately, what you're trying to do here is the BMS is trying to basically control and manage the health, welfare, and reporting status of that cell block that we looked at before. And you can't do it in the same way as you used to do with old lead batteries, because the discharge curve, a fundamental discharge curve of a lithium cell is flat as opposed to a nice, even, gradual slope. One of the unique, actually, I'm going to skip ahead to this slide first. So here is a specific example, okay, of one of the things you can do when you have that control mechanism and you have the ability of the batteries to be communicating directly with the inverter charger. In this particular case, one of the fundamentals we do is we have the function called dynamic charge controlling. Whenever our battery is connected by communications to an inverter platform, and call that an SMA Sunny Island, call it a Victron, call it a Solarc, or call it an XW Pro, and we're communicating with that inverter charger, whenever there's a charge source available, we take over and become the master and dictating the charge voltage set points that that hybrid inverter is going to respond to and output. By doing this, we are able to both manage the optimal health of the batteries, charging them as the battery cells, you know, want to perform to and respond to. The BMS is able to, you know, is looking at all those hundreds of cells, their maxes, their minimums, their cell spread, etc., and it's able to algorithmically calculate what the optimal charge voltage would be for those, to both recharge the battery quickly and in the most safe and healthy manner. So it's a, you know, a fairly useful feature that our batteries take over and control those set points dynamically through the charge cycle. In doing so, not only are you getting the health of it, but we're able to ramp up the charge voltage if the batteries are well within tolerances, temperature, cell spread, etc. And we're able to get recharge improvements. So in addition to the fact that we're a 1C battery and the current is not limited, we're also able to dynamically change the voltage set points through the recharge cycle to reduce the recharge time by up to 30%. You can see that in the graph, and you'll see the kilowatt gains there over charge in the gray area between the two graph lines. Okay, this is in addition to reporting things continuously like SOC and otherwise. In a battery, be it lead or lithium, that is not communicating with that inverter charger, it's got what we call a static voltage. In other words, you go and program that inverter charger to charge at bulk at, say, 54.4 volts, and then to float at 53.6, but it's capped or maintained statically at those voltage set points and won't rise above or below unless there's a trigger on there, like going to float mode or float stage. Okay, this is one of the advantages of having direct communications. One of the second things is that when you're looking at a lithium system, and again, you cannot approximate the remaining capacity of those batteries, if you're able to broadcast SOC directly to the hybrid systems, well, they all have cloud services. In this particular one, we're looking at, you know, some of the graphs and data that's available for you from a Connect Insight 2 cloud portal, but it would be no different than the Sunny Island cloud portal or the Solarc's monitoring for remote devices and things. You can find out your battery's accurate status, getting into the details, whatever details that cloud service allows, into cell spread, you can get into cell temperatures, you can get into the SOC reporting over time and have historical logs all logged there on their cloud service. So you can look at your system holistically from one particular point. If you don't have direct comms reporting with this, the only thing you're going to see on these cloud portals is the inverter's approximation of those battery statuses as understood by state or by voltage triggers or VDC. And again, we know that with lithium, voltage is not representative of SOC. So you have a very hard time getting really insightful feedback from your cloud services that's gathering this information. Okay, when we're digitally providing that information to the hybrid inverter charger systems, it's all being pushed up to the cloud and managed in conjunction with other things like your generator output, your AC loads, your solar harvest, and you can overlay all those to see how they all work in a combined interactive system. Not possible if you don't have comms, as you're only getting voltage readings, and those are only reported by the hybrid inverter. Some of the other things that are important here, and these are sort of snapshots of what you may see to a varying degree in these batteries. But if you have a battery with a BMS on top, suffice it to say, it's all managed by digital controls that are taking readings from within that cell block and all those hundreds of cells and providing information and data logging that on a continuous basis. Okay, having access to that historical data from a battery can be very, very powerful in terms of looking at, at the macro level. If you're looking at this data that's exported, let's say, to a cloud portal, you can help your customers with ongoing system design and maintenance. And most of you installers that have worked in Offgrid understand that you're practically married to your clients once you install an Offgrid system. You don't just install it and walk away and your job's done. They become your client for life, and there's ongoing, service and troubleshooting, and you're there as their assistant throughout the life of that installation. Okay, if you're able to look at some of the data there on these cloud services, it can help you with system design over time. Perhaps they've added more devices and more loads in their house, and they need to increase their solar array, or the size of their solar array, or increase their battery capacity over time, or even get into adding another inverter. All those things can be assessed by looking at their overall system performance. Well, if you ever have specifics on a battery, or if the battery is change over time, for instance, if we release new firmware and things, it's important to be able to get into that battery and access that data itself. So all of our batteries will have a USB port on them, and whether you're reporting this over the cloud to a connected system like a Solarc, a Schneider, or an SMA, or whether you're using this in conjunction with a platform that doesn't have the comms integration like an Outback Radian, you can still get access to all that battery's log data from our battery. And I believe that's unique out of the batteries we've talked about before. There's no USB ports on a Simplified battery, so you don't have access to that information. Similarly on the Fortress and other batteries, be it Battleborn, be it Rely On and other ones, they will have or they won't have access to that battery data. In our particular case, you can plug in with a laptop to any one of our batteries. You can upload or new firmware to it to increase the battery's capabilities and improve those over time as we make improvements, so the batteries are not static through the course of their installed lifetime. Correspondingly, you can also go in if you think there's an issue with the battery, and you can download the data logs, send them to us for review, and we can do analysis. It allows you to do graphic analysis like we see with the Python script here in that graph that'll show you, voltage, SOC, battery temperature, cell spread, and relay state over the course of that battery's life. And you can look at that in snippets or windows ranging from a day to multiple years. Okay, but that data is available to you, and data is powerful. We show you on our websites in some video instruction how to take advantage of that and use these systems to their fullest, how to install the software to extract the firmware from our websites and install them on new batteries, or to pull the data logs out of existing batteries. All that's there in video tutorial, and it's very straightforward, but it's very powerful if you look into it and learn how to do it. So we encourage you to do that. Okay, well, as you can see here, the last time I delivered this presentation was in Puerto Rico. In Spanish, just again, thank you very much. I think we're at our time limit now. And Hannah, thanks for putting this together. I guess we can open the floor to any questions.